next chapter is work, power, and energy. Okay, so let us define the terms one by one. So, if I want to define what is a work, basically in physics, work is associated with a force and the displacement. Right? When you apply force on some object, if work is done, then there has to be a displacement. Okay, so if I apply force and I don't see the object being displaced by some uh, amount of distance or displacement, then you say there is no work done, right? So work is basically associated with a force and the displacement. Okay, so it can be uh, lifting up of an object. You apply force and the displacement is vertical, so that is possible. And when uh, you apply force to an object moves, so there is a work. So fundamental idea of work is that. So in everyday usage, right, we may say that man is doing work, but the scientific definition, no work is done by force acting on a stationary object. Right? You apply force and the object is not moving means there is no work. Right? That is scientific definition. All right. Now let us see the work done. There are mainly three methods of finding the work done by a force. Right. So that is the next objective, to find the work done by an object. Right. The first category will be work done by the force being constant. Okay. So the constant force is our first case. Second case is the force varies with the time, right? Initially, I apply 2 newtons, after 1 second, 3 newtons, then 6 newtons. You see, it's varying, right? So, variable force. This is variable force. And then the next category is work done by the area under the force displacement graph, right? We can try to find the work done by by looking at the area under the force versus displacement curve. So three different methods do exist here to solve the problems. So let's look at one by one. The next concept will be the first one, that is the constant force. Work done by constant force. Right. So fundamental equation, there is a force and there in some direction you have a displacement. So work is equal to F dot S. F is a force, S is a displacement. Whenever you try to write this is the force and S vector denotes the displacement. Right. So dot product. So how do you find out a dot product? That is F into S into cos theta. Magnitude of the force multiplied by the magnitude of the displacement into the cos of the angle between them. That's the definition of the cos theta. So theta is, it denotes the angle between the F vector and the S vector. Okay, so using that we can easily calculate. So there are definitely some special cases. The special cases are dependent on the theta itself, right? Let us say theta equal to 0, right? So cos 0 is 1, so work done is simply F into S, right? Cos 0 is 1, so this is normally the maximum value of the work. Whenever whenever the force and the displacement are in the same direction, theta is 0, maximum work is done. Okay, then let's take another case where theta is 90 degree, in the sense, right, force is in one direction, the displacement is in the opposite direction, not opposite, 90 degree to that. Cos 90 is 0, so you see the work done is said to be 0, no work done. Okay, and the third case is theta is 180 degree, cos 180 is minus 1, so work is equal to minus Fs. So this is the minimum, right, amount of the work done. Okay, let's quickly solve a problem based on this. Now you see, from the basics of vectors, we know that the dot product is a scalar. So work done is going to be a scalar and it is measured in joules. All right. Okay. So this is the question. A body moves from 2 comma 4 comma minus 6 to 6 comma 4 comma 6 comma minus 4 comma 2 during the action of a force F denoted by 2 into I cap plus 3 times J cap minus K cap newtons, right? Find the work done. So what's the amount of work done? So the displacement needs to be found. So you have to find the displacement first. So the displacement is, this is something like A, point B. So from A to B it moves. So the displacement vector has to be found by destination minus the source, right? So that is 6 minus 2, the x component into I cap. Then -4 into j cap plus 2 minus of minus 6 is plus 6 into k cap. So this should be coming first, then this is coming. So subtracting 6 minus 2, minus 4, once again minus 4, 2 minus of minus 6 is 2 plus 6. Okay, so S becomes equal to, this is 4 I cap minus 8 j cap plus 8 k cap. So this is a displacement vector. Now work done is equal to the force vector dot product with this. So write a force that is 2I cap plus 3J cap minus K cap dot 4I cap minus 8J cap plus 8 into K cap. So dot product means all the terms with I can get multiplied. So 2 into 4 is 8. Then plus 3 into minus 8 minus 24. Then minus k into minus 8, k is minus 8. Alright, 8 minus 24 minus 8. So plus 8 minus 8 cancels. This is minus 24 unit joules. Next. If the force denoted by F minus 2I cap plus 6J cap plus 8K cap moves the body from A to B and then B to C, find part A of the question, work done along AB, work done along BC, part C of the question, the work done if the object is moved along the direct path AC. Okay, so here A is given. A is equal to 1 comma 2 comma minus 5. B is given as 3 comma 6 comma minus 3 comma minus 6 comma minus 2. C is given as minus 4 comma minus 1 comma 0. So there is a force. Force is already given. So the value of force is mentioned. Okay, this is the force. Minus 2I plus 6J plus 8K. So there are three parts in the question, right? Whatever we did in the previous problem, we need to repeat now. So first part is move the object from A to B, calculate the work done. Simple. Next, assume that the object is at B now, move it to C, B to C, calculate. Fine. The third part of the question is consider the same force, but you are moving along AC, directly A to C, not A to B, B to C, directly calculate AC, right? In that case, what is the work done? Okay. Answer to part A is minus 29 joules. So the part B answer is 60 joules. Part C is 32 joules. So ideally expected value, when you add these two, you should get this. Now we can say it is 31, which is close. Okay. 28. Okay, if it is, then that is right. So it is minus 28. So then you can see it is 32, perfectly matching, right? Minus 28 plus 60 is 32. Okay. Okay. Next question. A block of mass 2 kilograms is pulled by a force 40 Newton upwards through a height of 2 meters. Okay, part A of the question. Find work done by the force. Part B is find the work done by its weight. So pretty unique question is part B. So normally we know that, okay, when we apply some force, yes, work is done. Now the question says that find the work done by its weight. Remember, weight is mass into the acceleration due to gravity. So that is actually a weight always acting, sorry, it's a weight which is a force always acting downward. So that is also a force. So only because of that, this is said to be the work done by the weight. So question is very proper. All right, let's try to solve this question. Okay, now first calculate, let's calculate the weight, right? Weight is equal to m into g. Let us say that the g is equal to 10. So mg, that is a weight, 2 into 10, so that is always a 20 Newton force acting downwards. Now work done by the applied force, right? Let me call that as W by the force, because that's a part A. Work done by the force is nothing but the force into the displacement into the angle between them. So force is equal to how much? Force is equal to 40 Newton. All right. Force into the displacement. Displacement is 2 meters. It is mentioned into, see, both are in the same direction. Okay, let me write a diagram quickly. So this is the mass, right? This is the weight. This is the force, and this is the displacement. So force and the displacement are in the same direction. So 40 Fs into cos 0. So this is nothing but 80 joules. Straightforward answer. But the part B is work done by the weight. I'll write W. So that is equal to force. What is the force now? Force is equal to 20. Weight is 20. Right? Into the displacement, that is 2. And you see the direction. Work is downwards, displacement is opposite, right? That means there is a cos 180-degree difference. So minus, so this is minus 40 joules is the required answer. Right, next question. All right, let's move to the next topic itself. So that's the type 1, which is the work done by a constant force. Right. The next topic we are going to look at is called as the work done, a variable force. Okay. Now, the variable force refers to something like this. That is, we have the force denoted by the variable force is denoted by, let's say, f of x, right? And because of this change in the magnitude of the force, every time the magnitude changes, the distance or the displacement curve is, right, the small amount of displacement is dx, right? Then the small amount of work done by this is given by f of x into dx, right? Force into the displacement, right? This is a small amount of work. Okay, the w is not vector. So, anyway, let me remove the vector notation completely. Right. This implies if you want to calculate the total work, the w is nothing but integration of dw. So that is integration f of x dx. Right? We will normally put the limits, right? When the object is moving from x1 to x2, right? Because of there is an object here, I apply a force f of x here. This from A to B, the object moves. So this is being the displacement, right? You see that, right? From x1 to x2, your body moves like A to B, x1 to x2. It moves through that much distance. That's why this is the equation to do that calculation. All right, let's quickly solve a problem. If a force 2x, if a force 2x displaces an object from x equal to 3 to x is equal to 5, calculate the work done. So W is equal to integral, whatever is the x value. So that is 3 to 5. Find f into dx, right? So f into d. Okay, let's write the equation once again for our reference. Okay, so the equation says this is from x1 starting point to the x2 destination, the force into dx. This is the equation. So this is from 3 to 5, force that is 2x into dx, right? So 2 is a constant. When you take it out, x dx is there. Integration of x dx is x square by 2. Okay, so this is x square divided by 2, right? Substitute the limits from 3 to 5. This 2 cancels. That is 5 square minus 3 square. So 5 square is 25 minus 3 square is 9. So 16 joules is the required answer. Very straightforward. then we have a very special case uh, of work done by a variable force when it comes to the work done by a spring. Okay, all right. So work done by a spring. The general equation, let us say, let's try to write a diagram here to understand the whole concept. Okay, this is a reference. Okay, there is a object placed over here. Okay, this is the reference as I already mentioned. Right, and let us assume that we have a spring that is connected, right? Let me say that this point is, this is the point where x equal to okay, say some point x1. Let me mark it. This is x1, and what I do, I'll apply some amount of force, right? So I apply force in this direction. So because of force being applied, what I know that the object moves. Spring will expand. So because of the expansion of the spring, I have the block being moved to its new position. Let me draw it again. So there is a the object being replaced. Object moves to its new position, something like this, right? So the spring will look something like this. So now this is a new position x2, right? Force, because of this force, the object has moved. But you see, the string actually has has a tension in the string, right? The tension over here. Because of this, it will not move normally as if it moves when there is no spring. Right. So the work done, the spring is going to do some work over here. That work done by the spring, right? dW is equal to the F into dx. That is actually denoted by minus of k into x. Okay. X is the displacement and k is called as, the k is called as a spring constant. Depends on the string. Okay, now, so therefore, W is equal to integral x1 to x2. Initially it was at x1, it will move to x2, the f into dx. But f into dx is nothing but x1 to x2. I'll write a minus outside, k into x into dx. So minus k moves out, minus k goes out. And what happens now? So x, right? Okay, this is x square by 2 from x1 to x2. So this is equal to minus k by 2 into x2 square minus x1 square. That is equal to, minus you can take inside. So that is k by 2 into x1 square minus x2 square is the work done by the spring. The question is the work done by a spring if okay, work done by a spring acted upon by a force by a force whose spring constant is 0.85, which moves from x equal to 1.5 to x equal to 0.75, right? You can x1, this is x2, right? Directly we know the answer. W is equal to k by 2. So 0.85 divided by 2 into 1.5 square minus 0.75 square. Customer 8, yeah, 80. Okay. So the answer is 80.5 joules.